Hi, I'm Mark Barsamian with the Ohio University Math Department. In the previous video, I discussed plane separation. I started with a discussion of plane separation in drawings, the idea that a drawn line sort of splits the plane of a drawing into two halves, two half planes. We discussed the way that points and line segments interact with that drawn line in a drawing. Then I discussed the idea that in our axiomatic geometries so far, abstract geometry, incidence geometry, metric geometry, in those axiom systems, there's been no mention of any kind of analogous behavior being required in our axiomatic geometries. So if we want to have our axiomatic geometry exhibit that desirable plane separation behavior, it would need to be articulated in an additional axiom. So then I introduced the plane separation axiom, which articulates this kind of desirable plane separation behavior. And so again, that is not behavior that's guaranteed in any of our previous geometries, but it's a start. We've articulated with that axiom the desirable plane separation behavior that we would like to see. Well, in this current video, I'm going to discuss the fact that the Euclidean plane and the Taxicab plane and the Poincaré plane, those metric geometries that we have seen already, do in fact satisfy this plane separation axiom. They do exhibit that plane separation behavior that's analogous to the plane separation behavior that we're used to seeing in our old drawings. This video is produced for Ohio University Math 3110-5110 College Geometry. The reading material for this video is section 4.2 in the book Geometry, a Metric Approach with Models by Millman and Parker. There is no corresponding homework for this video. Let's recall some definitions from section 4.1. We discussed the partition of a set. To say that a collection of things is a partition of a set A means that these following three requirements are all satisfied. Each of the things in that collection is a non-empty subset of that set on the right. And furthermore, that set on the right is the union of all the things in that collection. So in other words, I can write that set A as the union of all of those A subscript i's. And furthermore, that collection of sets, A1, A2, A3, and so on, is mutually disjoint. That is, if you consider AI and AJ, where I and J are not the same number, then those two sets have an empty intersection. We discussed the definition of convex. A convex set of points in a metric geometry is a set that has this property. For every two distinct points in that set, the segment that connects those 2 points is a subset of that set. And in the previous section, we discussed the plane separation axiom. These words, saying that a metric geometry satisfies the plane separation axiom, mean this. For every line, L, in the set of lines, there are two associated sets of points called half planes, denoted H1 and H2, with the following properties. Property 1 is the three sets, the line and those two half planes, form a partition of the set of all points. Property 2 is that each of the half planes is convex. And finally, property 3 says if a point A is an element of half plane 1 and a point B is an element of half plane 2, then segment AB intersects line L. Now the goal of section 4.2 of the book is to prove that both the Euclidean plane and the Poincaré plane satisfy the plane separation axiom. Actually, I left out Taxicab plane as well. That's in there. Now, the approach taken by the authors is as follows. Define the sets that are the half planes in the geometry, and then prove that the geometry with those half planes as defined does satisfy the PSA, the plane separation axiom. The authors do this for the Euclidean plane, and they also do it for the Poincaré plane. The material is dense and difficult for a couple of reasons. The definition of the half planes for the Euclidean plane uses some new vector notation, And the proof that the Euclidean plane satisfies the plane separation axiom uses a lot of moderate to hard calculations involving vectors. The proof that the Poincaré plane satisfies the PSA involves a lot of hard calculations involving the hyperbolic trig functions. In this video and in our course, we will not cover those proofs. There are two reasons for this. First of all, the proof style is not one that we'll encounter again in the course. And secondly, the author's definition of the half-planes for the Euclidean plane is flawed. If you look very carefully, it's not really quite correct. But the main reason is this first one. The proofs are difficult and they're not productive in the sense that we won't be using that style of proof again anywhere else in the course. So what I will do in this video is instead focus on two things. I'll present clear definitions of Cartesian half-planes and Poincaré half-planes. I'll present the results that the Euclidean, Taxicab, and Poincaré planes do satisfy the plane separation axiom. Finally then, I will make informal drawings that illustrate examples showing how the Poincaré half-planes do exhibit behavior consistent with the plane separation axiom. I don't think that drawings of the behavior of the Cartesian half-planes are necessary. So I'll start with the definition of Cartesian half-planes. For real numbers a, m, and b, define Cartesian half-planes as follows. This symbol, capital H with a subscript a and a superscript plus, denotes this set, the set of all ordered pairs in R2 such that x is greater than a. This symbol, capital H with a subscript a and a superscript minus sign, denotes this set, the set of all points in R2 such that x is less than a. Those two sets are illustrated this way. Now there are two more sets. This symbol, capital H with a subscript m comma b and a superscript plus, denotes the set of ordered pairs in R2 such that y is greater than mx plus b. This symbol, h with a subscript m, b, and a superscript minus sign, denotes this set, the set of all ordered pairs in R2 such that y is less than mx plus b. Now these two sets can be illustrated. Now, note that the book defines Euclidean half-planes rather than these planes that I'm calling Cartesian half-planes. This is just a stylistic choice. The resulting planes are the same. But I think it's important to call the half-planes Cartesian because their definition only uses calculations involving Cartesian points and lines. It does not use in any way the Euclidean distance function. But also note that the book's definition of their Euclidean half-planes uses vector notation, including some symbols that we've not used before. And a careful reading of the book's definition will show that there is a significant flaw in it. But mainly, stylistically, I think it's important to call these half-planes Cartesian, because we'll see that they actually can be used in Euclidean geometry, but also in Taxicab geometry. Now for the definition of Poincaré half-planes. For real numbers a, c, and r with r greater than 0, define the Poincaré half-planes as follows. This symbol, capital H with a subscript a on the left and a superscript plus on the right, denotes the set of all points in the Poincaré plane, that is the upper half plane, such that x is greater than a. This very similar symbol with the superscript minus sign denotes the set of all ordered pairs in the Poincaré half-plane such that x is less than a. Those sets can be illustrated easily. Now there are two more Poincaré half-planes. This symbol, capital H with a subscript c on the left, subscript r on the right, and a superscript plus on the right, denotes this set, the set of all ordered pairs in the Poincaré half-plane that have the property that x minus c quantity squared plus y squared is greater than r squared. This symbol, very similar to the previous one but with a superscript minus sign on the right, denotes the set of all ordered pairs in the Poincaré half-plane such that this inequality is true. X minus c quantity squared plus y squared is less than r squared. These sets can be illustrated as well. Now you see that the points that are in the red set are the points whose distance from the center of that semicircle is greater than r. The points that are in the green set are the points whose distance from the center of that semicircle is less than r. Notice that my symbols for the Poincaré half-planes differ from the symbols that the book uses. The book just uses an h plus and an h minus. I use symbols that indicate which kind of line is associated with these half-planes. These two symbols denote half-planes associated with a type 1 Poincaré line. These two symbols denote half-planes that are associated with a Poincaré type 2 line. If we go back to the Cartesian half-planes, notice that my symbols indicate which kind of line those half-planes are associated to as well. These symbols indicate that those half-planes are associated with a vertical line. These symbols indicate that those half-planes are associated with this non-vertical line. Now that we've introduced the half-planes, we can introduce these propositions. Proposition 4.2.4 says that the Euclidean plane satisfies the plane separation axiom. More precisely, using those Cartesian half-planes, HA plus and HA minus, or HMB plus and HMB minus, with those Cartesian half-planes playing the role of half-planes for the vertical line L subscript A or the non-vertical line L subscript MB, with those half-planes, the Euclidean plane does satisfy the plane separation axiom. The proof of this proposition is provided in the book on pages 72 to 73. The proof shows that the Euclidean plane does indeed have properties 1, 2, and 3 of the plane separation axiom. Remember that the plane separation axiom has these three requirements, 1, 2, and 3. The book uses a different definition of half-planes than I'm using in these notes, as I mentioned before, so the book's proof looks a little different than the proof would need to look in these notes. But here's an outline to the proof that would be needed. We'd need to first of all prove that the Euclidean plane satisfies that plane separation axiom part I. That is, we'd need to show that this set, the vertical line and those two half-planes, is a partition of the set R2, the set of all points. And we'd also need to show that for non-vertical lines, the set consisting of that non-vertical line and those two associated half-planes is a partition of R2. All of that would be the proof that the Euclidean plane satisfies the plane separation axiom I. Plane separation axiom II is that the half-planes are convex. So the proof part 2 would need to be a proof that those Cartesian half-planes are indeed convex sets. And then finally, the proof part 3 would need to be the proof that the Euclidean plane does have this property that if you have a point A that's in one of the plus half-planes and a point B that's in one of the minus half-planes, then the segment that connects A and B does intersect that line. And the proof would need to show that that happens for vertical lines and their associated half-planes, and also for non-vertical lines and their associated half-planes. Now it is a result of an exercise 4.2, number 5, that the taxicab plane satisfies the plane separation axiom. Now the exercise doesn't mention specifically the half planes that you would use, but that's why I referred to the half planes in these notes as Cartesian half planes. Those symbols, h subscript a plus and h subscript a minus and HMB plus and HMB minus, I called those things Cartesian half planes. They can play the role of half planes for the taxicab geometry as well. Now, as with the Euclidean plane, these half planes with that symbol play the role of half planes for the vertical line with that symbol. Whereas these half planes with these symbols play the role of the half planes for the non-vertical line that has that symbol. Now, when discussing segments, rays, angles, and triangles in Chapter 3, we did not discuss how those objects look in the taxicab plane, but in fact, all those objects look just like their Euclidean counterparts. So because of that, I won't make any drawings to illustrate the taxicab plane and its half planes. The proof that the taxicab plane satisfies the plane separation axiom would be very similar to the proof that the Euclidean plane satisfies the plane separation axiom. Proposition 4.2.5 says that the Poincaré plane satisfies the plane separation axiom. Now for the Poincaré plane, we use these Poincaré half planes with this symbol or this symbol to play the role of half planes for the type 1 line that has this symbol. And we would use Poincaré half planes with these symbols to play the role of half planes for the type 2 line that has that symbol. And this proposition says that the Poincaré plane with those half planes described does satisfy the plane separation axiom. Now there's a proof of this proposition on pages 73 to 74 of the book. The proof is a very interesting application of the hyperbolic trig functions, hyperbolic secant and hyperbolic tangent. And the proof also uses the intermediate value theorem. I won't discuss the proof, but here's an outline. The outline is just like the outline of the proof that the Euclidean plane satisfies the plane separation axiom. In part I of the proof, you would need to show that this set, consisting of the type 1 line and these two associated type 1 half planes, is a partition of the Poincaré half plane. And you would need to do the same thing for the type 2 Poincaré line and its associated type 2 Poincaré half planes, show that those three things are a partition of the Poincaré half plane. That would be part I of the proof. Part II of the proof would be the proof that the Poincaré half planes are convex sets. And finally, proof part III would be to prove that if A were in one of the Poincaré type 1 half planes with a plus, and B were in the associated Poincaré type 1 half plane with a minus, then Poincaré segment AB intersects that line, that type 1 line. And similarly, show that if A is in one of those Poincaré type 2 half planes with a plus, and B is in the associated Poincaré type 2 half plane with a minus, then the Poincaré segment AB will intersect that Poincaré type 2 line. Although I won't discuss the proof of proposition 4.2.5, I will make some drawings to illustrate how Poincaré planes do exhibit behavior that's consistent with the plane separation axiom. First, I'll start by making some drawings showing how the Poincaré plane satisfies PSAI. Well, we've actually already got some drawings that will work for this, so I'm going to go up and look at them and copy them and bring them back down. These drawings of Poincaré half planes will work as illustrations, so I'm going to copy these and bring them down, and when I scroll back down, we'll find them down below. So there are those drawings from above, copied here. So these drawings show that if you drop a point anywhere in the Poincaré plane, say here, or here, or here, it's going to land in one of those sets, exactly one of those sets. So those three sets form a partition of the Poincaré half plane. Same thing for these type 2 half planes down below. if you drop a point anywhere in the Poincaré half-plane, say there, or there, or there, it's going to land in one or the other of those half-planes or on the line itself. So these drawings are not a proof, they're just simply an illustration showing how the Poincaré plane does satisfy PSA I. Now I'm going to make some drawings showing how the Poincaré plane satisfies PSA II. Remember that axiom says that the half-planes are convex. Well, I'm going to show a drawing that illustrates how Poincaré type 1 half-plane with a plus sign is convex. Now remember that the statement of convex is a conditional statement that says that if 2 points are in a set, then the segment that connects those 2 points is a subset of that set. So to illustrate that a set is convex, I think it's helpful to use 2 drawings. So I'll make 2 drawings here. So there's an illustration that shows if 2 distinct points, A and B, are in that type 1 half-plane with a plus, then the segment that connects those 2 points is a subset of that same half-plane. Now notice in this drawing on the right, segment AB is a subset of that half-plane. Line AB is not a subset of the half-plane. Line AB goes on over into the other half-plane. So the drawing should be clear. Show the segment and then also show the symbol for the line. So the statement that the half-plane is convex does not say that line AB is a subset of the half-plane. It says that segment AB is a subset of the half-plane. Now I'll make a drawing that illustrates how this Poincaré type 2 half-plane is convex. So again, I'll make 2 drawings. So there's a drawing showing 2 points A and B that are both elements of that Poincaré type 1 half-plane. And then this drawing shows that segment AB is a subset of that same Poincaré half-plane. And again, it does not claim that line AB is a subset of that half-plane. It's not required, but the segment is. Now the only surprising drawing is the one that I'm going to make now, that Poincaré half-plane type 2 with a plus is convex. Now at this point, before going any farther, think about these shapes. If you were thinking about this pink set as a set in the Euclidean plane, you might think that it is not convex because you would expect that the segment AB would look like this. And that segment AB would not be a subset of that pink half-plane. But that drawn red stripe is not Poincaré segment AB. That's Euclidean segment AB. To draw Poincaré segment AB, you have to first imagine Poincaré line AB. There's Poincaré line AB. Now I can draw Poincaré segment AB. So we see that Poincaré segment AB is a semicircular arc that's part of that semicircular line AB. And you see that that Poincaré segment AB is a subset of that same red half-plane. Finally, I'll make some drawings showing how the Poincaré plane satisfies PSA 3. I'm going to start by drawing an illustration showing that if point A is in that Poincaré type 1 half-plane with a plus, and point B is in the Poincaré half-plane type 1 with a minus, then the segment AB does intersect that Poincaré type 1 line. So on the left you see a drawing showing points A and B in opposite half planes of that Poincaré type 1 line. And in drawing number 2, you see segment AB intersecting that line. Notice in that drawing I've highlighted that point where the segment intersects the line. Now in fact the second drawing might be clearer if I did not include the half planes, because the then part of the statement, Poincaré segment AB intersects that type 1 line, that statement doesn't mention anything about the half-planes. So in fact, in this right drawing, I'm going to get rid of the drawings of the half-planes and just include the things that are mentioned in this statement. Now you see that that right drawing only includes objects that are mentioned in that statement. Finally, let's make a drawing for this statement. If point A is in that Poincaré type 2 half-plane with a plus, and point B is in the corresponding Poincaré type 2 half-plane with a minus, then Poincaré segment AB intersects that Poincaré type 2 line. So again, I'll make two drawings. So there on the left you see a drawing of the hypothesis, the statement that A is in Poincaré type 2 half-plane with a plus, and B is in the corresponding Poincaré type 2 half-plane with a minus. And on the right, we see an illustration of the conclusion. This illustration on the right only includes the objects that are mentioned in that conclusion. We can see segment AB intersecting this line, and the intersection is highlighted by the fact that I've drawn that point at the point of intersection. Well, that's the end of the video. Thank you.